Um, Hello there. Yeah, it's time to go. Episode number, I don't know, 5 maybe or 4. And we decided to do an overview of the GitLab Agent project, of the repository and the code structure. And maybe Timo will have questions, or we'll have things to talk about. Let's see. So this is the repository. Like, I don't know what exactly to talk about, so I will just start somewhere and then we will go somewhere from there. So we have two binaries that are built from this repository. These are CAS and agent K. They are here in CMD. Then we have some documentation in the doc directory. This is mostly technical design decisions that we document. We try to document anything non-trivial here. Then, I don't know, some examples. I think these are Git modules pointing to some other repositories. I haven't looked at them for quite a while. Then PKGs, like exported packages, like public, theoretically for public consumption, or public API to some extent. These are CAS configuration, protobuf for CAS configuration, then protobuf for agent K configuration, the one that's stored in the Git repository, the agent configuration repository. Then we have the generated docs here. Thanks, Timo. Then we also have, so for CAS, we also have the config example YAML. This is generated based on this test. Well, this test constructs an object, like minimal configuration, and then it validates that the contents of this file match the minimal configuration with defaults applied. And the test fails if it doesn't match. So it's like an example of not the minimal configuration, but it shows the defaults that are encoded in code. It's convenient to give a link to the file and to a particular line and say, hey, this is the default value, rather than digging through code. Yeah, so this is basically all defaults. And I also leave comments here in certain places where this is the default. Well, no, this is the parameter that can be put here, and also some required parameters are here as well. Anyway, what else? Yeah, docs as well. Thank you. And then this is the Ruby generated Ruby gem, so that for the gRPC APIs that are exposed on the private API endpoint, these are for consumption by the Ruby on Rails. So when Rails talks to CAS, it uses this gem with generated Ruby code. It's all here somewhere. Yeah, these are the APIs it can use, like, and does use some of them, or all of them maybe. I'm not sure. All of them probably. So what else? The internal, which I skipped, is the code for everything that is not in PKG and not in CMD. So API is just internal API types that are used throughout the code base, which are not too many, like our domain API types, token, information about the GitLab server, information about an agent. This is used by CAS, not by Agent K, by the way. It's like information about GitLab repository and so on. We get this from Rails, basically. Information about the project. This is for GitOps. Again, information about where in GitLab this lives. This types is imported from GitLab. We have a dependency on GitLab. GitLab is GitLab's gRPC wrapper around Git, to simplify it a lot, but that's the main thing, main feature of it. And then it's just a helper function. And then the next GitLab is things to talk to GitLab, like special, any code that we use to talk to GitLab or parse responses or anything like that, fetch files, like visit a directory with files, pull a repository, pull connections to GitLab because GitLab is multiple servers and we establish gRPC connections to different servers. It's a pull basically. And we have reference discovery, copied and modified, optimized for our needs. Then that's it for GitLab. Then this is a GitLab client. This is the GitLab client we use, but it's a GitLab client, one of a few. So it's basically a wrapper around standard library HTTP client with functional options pattern applied. Plus, we have a few convenience response handlers which allow you to like read the response, unmarshal it into an object, and blah blah blah, handle different things. Yeah, nothing super interesting. Then this is an interesting directory, a little bit interesting. It's things that use this client to make concrete API calls. Like this is the GitLab Agent info API call. This is the response from the server. Like we unmarshal it into this struct, and this is like the function that is called. It gets the client, token, and options. And then this is the interesting kind of business logic of this function. And then it just populates the response from, like, populates an object it returns based on this response. So this is an internal kind of thing to this package. As you can see, it's unexported, and it returns an API type which looks slightly different to this struct. Yeah. Yep. Then that's the whole directory is like that basically. I'm not sure what is. Okay, that's another helper and another thing. Yeah, and then we also have this API proto, which is it defines the structs for interaction with the API, but I'm not sure why this one is not defined there. Maybe
other ones use API. If you open like the get project info or something, they will.
Response.
Okay, that's even.
Okay. Okay. This one defines it only for this one, allowed agents, and this is because of something. Because we reuse the type from configuration. So to avoid duplication, basically, that's why we just use it. Maybe I should like change all of them to be defined here in the proto proto file. Now it's basically only this one, which is used here. This is what the generated type. Yeah, maybe we should change all of them. But yeah, this one is like that because I wanted to reuse the prototype message. And I don't remember why I didn't use the concrete type rather than this one. Yeah, there was a reason, I don't remember why. Well, it's convenient actually because validation code is generated, right? With handwritten types, we don't do any validation here. And with this one, we do validation. So I think we should probably change all of them so that we can define validation rules in in the proto file and then validate them. So I think that would be good. Anyway, this is the GitLab client module, and then this is the meat of the project. So it's modules that it's a way to compartmentalize functionality into building blocks, and this described here in this README. No, it's not here. It's described in the doc modules. Yeah, this is described. This describes what it is. Well, it's a directory with directories, but each one is, where is a good example? Maybe this one. You have stuff that's part of the agent and stuff that's part of the server, and then you have an RPC that they use like to talk to each other. That's basically the canonical example of a module. And then we just call them agent module, server module, but this whole thing is a module. Then they may have shared both agent and server are optional, that you don't have to build both if you don't need both. Like configuration is only one, the server, and configuration for a client is a pretty special thing. So we have like a helper to watch configuration, but the agent kind of contains code that calls this watcher in the main application code. Basically, it doesn't have a module for configuration. At least that's how it's currently structured. Basically, the most special thing is the least likely it is to be a module here. But anyway, I try to structure things like this. And if you look here, we have well, RPC defines service, RPC, and then messages, then server. Okay, let's look at how modules, server or agent, what structure they have. So they have factories. Factory is what is used to instantiate a module. It's instantiated only once in the beginning of the program. And then actually, let's look at the module interface. This is the server module. Interface of a server module. So once it's instantiated, you have run and just the name to get the name of the module. Obviously, this is the interesting method on a module. And it's executed in a separate Go routine to execute the code of the module, obviously.
So is it always that a module is executable or an actor, or can it be that a module is just shared for business logic to other modules, which are?
So for sharing code, we have that case. We use not modules, but sorry, one second. Ладно, я разговариваю.
Это из 3.
Мгм. Ага. Ладно. So we have such case, and maybe not even one. So some things have code in the root when it makes sense. This one is used in a few other places. And then some have code, as I showed you, in RPC, because it's kind of part of RPC. This thing is a way to use the RPC. And we also have cases where we have sub packages for sharing for sharing code. Well, it's described in the doc there, but yeah. So there is a factory. Actually, factory also has a type. So types. I should have started with this. Sorry, types for agent and server are defined in these directories, and then there is a separate directory with shared types. And it's like just shared things that make sense there and there. Like API for doing things. Like an internal API between the host program and a module. So like modules interact with the host program, basically. It's similar to actors, maybe, in some sense. And then some types here, agent meta information. It's because agents send information about themselves to the server, and this is done via an RPC. So this kind of lives here as a shared thing, which is used by both server and client and agent. And there are a few other things that are shared. And then for server and agent, we have APIs and other things that make sense for modules. So API for server, we have various constants, this is one of the important things, configuration. So the host program class gives this configuration struct to each module when it starts the module. And the same with agent, actually. Agent host program gives configuration. And then this is the shared API. And then, so I have two kind of APIs, one for, let's start with this one. This one is, you can get it from a context if you are inside of an RPC handler, and this one is given to you from a config. And then we have, like, this is the server API, and this is the factory, and wow, obviously what this is. And let's look at the agent API as well. Same kind of similar stuff, configuration and various stuff, module, RPC API, factories. So here we have one more interesting thing. This is a leader module. So a module can implement this interface, which it just needs an extra method. And this is the same thing, just extra doc here, basically. So this is if a module wants to only run when a particular configuration is given to agent, and it wants to run only when only one instance should be, if only one instance should be a leader, then you implement this method, and the module participates in leader election, basically. And it's only ran if this instance of agent K, this pod of agent K is a leader, is a leader that is elected. So we use the standard client Go leader election code to do that.
So does the server also has this leader concept, or is it only for the agent?
server doesn't have it. Only the agent has leader election. The server doesn't need this, didn't need this so far, and also the server doesn't have to run inside of the cluster. I mean, it can and it does on GitLab.com, but it doesn't need the cluster at all. Doesn't matter where it runs. So yeah, this is a unique thing for agent API. And what else? These things for making requests to GitLab. There's helpers to construct a request, and the request is defined somewhere here, response, and request is somewhere here, request config. Yeah, this one. Okay, so we have this kind of API kind of things, and then the rest are actual legitimate modules. And they do use, some of them use each other. Like and then we have the tool directory, which contains various utilities, helpers, and stuff.
And these are these vendor things, or is it?
Sorry, what was that?
Are these vendor packages, or
no? Okay. These are handwritten artisanal packages.
Okay.
Yeah.
So why do we need a math C package? Like what's in there, for example?
It's just, wait, no, this is the wrong one. Math C. Just a wrapper around the standard wrapper generator to make it thread safe, because the standard library is not thread safe. And also we have a helper, or two helpers,
right
here in this particular case. And then we have other things that nothing super interesting, but some of the things are used by both server and agent. Some things are not.
Okay. Yeah.
Anyway, tools directory. Here, an interesting thing is testing. This is where we have helpers for unit and whatever tests, and mocks start with mock, and Kubernetes testing, and for various testing, and what this is, reproducer for a bug, I guess. I forgot about it. Anyway, this is the testing directory here. Well, another thing is build, is stuff for builds. And here we also have a KPT package to deploy agent K.
So why, I mean, I've seen that there's a separate chart for the agent, which is the one you would install when you follow the docs, right?
Yeah.
So when is this used? Just for like local testing, or?
No, it's not used for anything unless you are installing an agent. So it was there before the chart.
Okay. But if a user wants to install Agent K, they will use the chart exclusively, which doesn't depend on any of this here.
No, yeah. So maybe we should deprecate and delete this, but I don't know. It sits there, and yeah, maybe
maybe it's useful. Maybe it's useful if you want to install into a local cluster during development.
Yeah,
you need to keep it in sync though.
I did it a couple of times, but yeah, the problem is keeping them in sync, I guess. Yeah, maybe that's not the best. But we created it before the chart. Chart was actually contributed by someone else, like not a GitLab employee. So community contributor contributed the chart. So this is stuff for builds basically, and then here we just have plumbing for CI and other things. And here in the root we have various dot files, and obviously it's obvious what these are. Workspace is the basal workspace definition, and nothing particularly interesting. Okay, any questions so far?
Not regarding the structure. Looks pretty
Okay,
intuitive.
cool. Then, well, we have a make file. This is what we use to run all the commands. It's like basically a way not to type all this by hand. I think everybody does it this way, rather than using make to do sophisticated things. It's just a set of shortcuts with some documentation, actually. Well, I guess that's it. That's the overview of the repository. Do we have any questions? No. Any non-repository related questions? We have half an hour more. We can talk about anything here.
Yeah, I mean, it would be nice to maybe if you can walk us through but let's take an example. Like if an agent starts, how it connects to CAS, if it if it has like GitOps, how does it install a manifest? Like, go through the kind of the code and the critical pieces where it ends up and how it's implemented. That would be helpful.
Cool.
And yeah, we can take the example I made if it makes sense.
Yep. This is our main of the agent. We use Cobra and we run that thing. It's just various plumbing here, random generation, random seed, and the context tied to signals. Then we run the command. The command
It doesn't use the math.
Huh?
The random stuff didn't use the math package.
Well, it seeds the.
Wasn't there like a
global one because there are some libraries that use the global random generator.
Okay, that's true.
Like Kubernetes libraries use that actually, and I think, yeah. Anyway, this is more safety measure because some code somewhere can use the random number generator. Anyway, so the command is basically binding the flags, doing various setup, loggers, environment variables, flags. We try not to have flags here, but for some things they're inevitable. The main ones are these two. And CI certificate, and then for observability, another CI certificate, not CI certificate and key, and blah blah blah. Then this is the interesting struct. It's the constructed application from flags and environment variables. We also have very few environment variables that we need. And then, well, this is where we construct all the objects that are needed, like instantiate all the structs and compose the graph of the application. Like this is CAS connection, this is tracing, internal gRPC server, and so on, like Kubernetes client and everything that's needed for it. Leader election, for leader election, we are constructing modules, then we running the modules, like module runner, constructing the module runner, then we are registering modules with module runner. I'll go into details about each in the second iteration, but this is the overall structure. Basically, we are constructing all the things that we need, what the agent needs to execute, to run, and then we run those things. This is a library that I wrote a long time ago, but it's quite useful. It's super simple, but quite useful. So it starts things in Go routines, but then when it gets a signal from context, it stops them in reverse order. Like it waits for this to stop, so that and then it signals for this. This is just a function. Well, Go accepts a function.
And this Go just starts a Go routine somewhere, and
yeah. It just starts a Go routine basically, and gives it the context, and it cancels the context when it's time for this stage to terminate, and stages start to terminate when any of the functions returns an error, because this is a function that can return an error, or this context signals done. So it's a way to do ordered shutdown, because these things depend on these things, and these things depend on these things, and like so on. And the last to terminate will be the leader election, because modules use leader election, and internal server uses modules, so it starts after and stops before the modules, and internal modules can use anyway. This is like yeah.
On what is the internal server? It gets the stage passed, or what can it do with this stage?
It starts itself. Internal server is this struct with logic to construct the internal server and start the internal server on this.
So I'm more this stage. Why is it? How is it used? And
stage has a single method to start a Go routine.
Okay. I see.
Yeah. This is the implementation. It starts the function in a Go routine, and it cancels everything if a function exits with a non-new error. If everything was fine, then it just puts that into a channel. That's the stage. But then there's another thing that uses stages, but let's not go too deep into details. So this is the kind of how it starts, and this is what is needed to actually start. So connection to CAS is created here. We read token and blah, 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 certificates. These are the options for gRPC dial, virus interceptors, keep alive, and blah, blah, blah. And then let's skip this for now. And then we do a dial. So this is the overall structure of a typical gRPC dial. Nothing interesting, but this part is interesting. Here we support tunneling gRPC traffic through WebSocket connection. We use a library for WebSockets, which is called somewhere here. This is the library, and it gives us a way to, given a WebSocket connection, to have a net.con basically. So it takes care of all that passing and wrapping using binary messages. I wrote my own implementation, and then I found this library, and okay, I will just throw away all my code.
Is this only implementation the thing you find in the tools folder? There's a WS tunnel.
On top of that library, and on top of that net.con implementation, the thing that I wrote, and this is used here, is that dialer for gRPC thing. It uses that library to dial, and then it uses that library to do a netcon, but it gives the signature. This function gives a signature that is compatible with gRPC option.
Okay.
So we kind of give gRPC a way to dial using this library, and this library does all the networking. And gRPC just thinks it's a network connection, usual network connection. And then gRPC, that WebSocket library uses this HTTP client with this transport, with these parameters and TLS configuration and everything. And then we support proper unwrapped gRPC connection if you wanted to. But yeah, we use this one. Both work fine. So that's how we get the CAS connection. So if we are talking about GitOps as an example, GitOps is implemented as modules. And we have two, one for charts and one for manifests, like raw manifests, which are fetched from the repository. They work super similarly. So let's look at manifests because they were built before charts. So this is the construct modules method. And this is the list of factories to construct modules. And we just iterate through that list and call the new method providing the configuration. As you can see, this comes from that package with APIs and interfaces for agent modules. Config, yes?
And all modules get the same configuration, basically.
Yeah, the only difference is the logger. It contains the module name. Each yeah. Everything else is identical. Okay, no, agent API is also different because we also put a module name here, but everything else is identical. All the like CAS connection, internal server, all those things are the same. So we get the module, then this is the leader election thing, which maybe wraps the module. It just checks if that module is a leader module, and if not, then it returns it as is. If it is a leader module, we give it a wrapper which does some logic to check if it's a module which this module, given this configuration, wants to run or not. It dynamically starts it and stops it, and that's all.
Okay, so just for clarification, it's not the agent who's a leader or not, it's a module in an agent which is a leader or not. So if you have multiple agents, it could be that one module is a leader in one agent and the other module is a leader in the other agent.
No, one agent is a leader, other agents are not leaders. We don't have per module leader election, but each module in an agent can say, I'm interested in us being elected as a leader. Like if no one is interested in agent participating in leader election, then this agent will not participate in leader election. It will revoke its leadership if it was a leader. And this is then dynamic because configuration is dynamic. So based on configuration, different modules may need to, be a leader. To work, they may need this agent to participate in leader election. But actually, this was implemented. It all works. It's all fine. But then we have starboard vulnerability module, which it always says that it wants to participate in leader election. So all of that is kind of unnecessary because this one always returns true since a two ago. It used to depend on configuration, but now it doesn't depend on configuration.
Okay.
But anyway, maybe this will be removed because we had a Cilium module and it got removed. So maybe this will be removed someday, who knows? And that machinery that I built for leader election still may need to be conditional because otherwise we have the GitOps that also, it's probably a good example. Let's look at this one. It tells agent to be a leader only if GitOps is configured. So if there is no GitOps, then there's no need to become a leader unless other modules want to. So this is for leader election, and then we also have a branch here. Modules that use internal server are started before internal server, I think, or somewhere here. Yeah, we start the internal server first, and then we start the modules that use internal server, and shutdown is the other way around. We have a module that talks to the internal server. So if internal server has been shut down, we will get errors here, and we don't want that. So we shut them down in the reverse order. So yeah, anyway, we have constructed the modules. We return them separately because of that shutdown quirk. And then we have a module runner. This thing is responsible for fetching configuration. It establishes a connection to CAS and waits. And CAS eventually may send configuration. And then the module runner is responsible for pushing this configuration to each module, basically. And where is it? It's in a separate file. Yeah, so it starts the modules and it pushes configuration to modules. It also pushes it, it deduplicates it. So if a module hasn't received what we wanted to send to it, and a new configuration is available, we discard the old one and we only want to send the newest configuration. So it can happen that a module takes time to reconfigure itself when it gets new configuration because it was doing some whatever IO or something, and okay, and a new configuration becomes available. We don't want to block the sender, the module runner. Where is it? So we basically have this loop where if new configuration is available, we deduplicate it. Yeah, and here we do the same. We shut down the thing that pushes configuration and then shut down the modules that we run here in the reverse order. And then, yeah, this is the watcher where we watch for configuration updates, and then we apply configuration updates by first running all the defaulting on that configuration. Each module can contribute to defaulting of configuration. And then once all modules have applied their defaults and none of them returned an error, we use that configuration. We send it to all modules. Basically, that's how configuration is propagated. So a GitOps module gets configuration updates via the channel that is given to it here in the run method. It can ignore it if it doesn't care. The program won't block or break in any way. Also, that configuration channel is closed when the program should stop, when the module should stop, and the context is also done when the module should stop. But yeah, for GitOps, we have this structure here where we support GitOps manifest. So it's a list repeated. So it's a list of manifest projects. So we have a module, a worker manager. Basically, we have a Go routine, at least one, actually more than one, for each source of manifests. So they are applied concurrently. They have powered concurrently, and then yeah. So it's just a loop over the channel. We are given the defaulted configuration, and then we tell the worker manager to apply that configuration. So it shuts down workers, starts new workers, and starts and stops whatever needs to be done. Then each worker, we have a 3-stage thing here. This one is responsible for, maybe we should look here. So the watcher it pulls a repository here, pulls a repository, object watcher. Then once it gets an update, it pushes it into a channel. That channel, it's a classical Go pipeline, basically.
Yeah.
The channel is fed into the decode stage, which is here. Decode, it's in a separate file, decode file. They're all methods on the worker, but it's so much simpler to find it when they're structured like that. So this one gets the desired state here, tries to parse it with a retry loop, which is not a simple loop. It's like quite a complex loop. There are reasons for that, because the decoder might it might fail initially, but then like in the case with custom resource definitions, once they are
I understand.
established, then you can parse the manifest and blah blah blah. So we do it kind of in a loop with back off. So once everything is fine, we what is it? New job. Okay, this retry pipeline pushes the results of process. If they're successful, new job, pushes them into the jobs channel, second channel here. And that jobs channel is read by apply. So it's the terminal last stage of that 3-stage pipeline. And this one is, again, reading from that channel, and it uses CLI utils to apply. It also has a back-off loop. So it tries to apply them every 5 minutes, and with back-off if there was a failure. And apply is just apply a run. We give it the manifests with configuration according to the configuration file, and it applies them to the cluster and prints the output. Yeah, and that's how GitOps works.
And if now, let's say there's an error in the apply, you only get this printed, or is it somehow propagated to CAS, or like
No,
what happened?
it's only logged here, and this thing also prints some details, I think. We do have an epic and issues, and even the design for agent activity page, and we want to show such things like failures there on the agent activity page. We even have technical documentation to some extent about it, but we haven't defined the format, the proto definition for the event, and it wasn't a priority. So
Okay.
this is kind of stuck, but we do want to show it in the user interface, and maybe notifications and like whatever the design is.
Okay.
Currently technically there is a way to send information back, and it is used in vulnerability module and somewhere else as well, I think. But yeah, we just don't do it here, not yet.
Okay.
Should. So this is how it works in the agent. Let's look at the server. So they talk via gRPC, RPC service. This is the service GitOps, and it has the get objects to synchronize. The request here is a string, the project ID. Then it's the last commit processed to avoid sending the same stuff every time, only if commit changes. And this is the paths to scan. And the response is basically, this defines a finite automata for the response stream, because request is just a request, but the response is a stream of response objects, response messages. And so we have our own definition of a way to define finite automata using options on fields in a message. It's brought here, I think. No. Where is it? Not proto to gRPC to automata. So this defines a way to describe a graph of allowed transitions between fields. So it's a one-off field message, and it means basically the first is first, this one. You get a stream of messages, and the first has to be the first. Then allowed transitions are 2 or 3. So this one or this one. And then after each one is like 2 or 3. So this one can repeat because it allows a loop 2 to 2, and eventually to go to 3, and 3 can only go to E off. Or it can also be just E off if server decided to close connection, and that's a valid thing to do for it. And validation as well, various validation. Yeah, so that, and we also have, where is it? Stream visitor thing, which is the code that uses these options on fields to enforce that the stream follows this graph definition of what is allowed. So this is basically to prevent malicious people sending invalid messages and triggering unknown behavior in the server. It's protection for the server. But agent also uses that for some things where it makes sense. Again, to just ensure things always go as expected and not in a weird way, do it to bugs or malicious intent or anything. So this is the RPC, and the server is implemented here in the server module. Well, we have the watcher that uses this RPC. Yeah, it uses that stream visitor. And basically header object trailer 1 to 3, this constants, and it calls callbacks on header, on object, on trailer, and Basically, header contains meta information, object contains whole or a piece of object. Is if the manifest file is too big, it's chopped into sections, and then this thing concatenates them here in memory. And then trailers is just some bookkeeping. And then once it has consumed the stream, it calls the callback, which we saw in the agent module. It gets that object, the watcher. That's the callback that is called, and that this thing just pushes it downstream. So yeah, this is the, where was it? The watcher, object watcher. But yeah, the server. So the server also starts with the factory. It constructs the server. Factory constructs a module, and module uses this new server. Factory uses this new server, and it registers. Right, the module doesn't do anything because we construct the server in the factory and register it with the agent server. Agent server is just the gRPC server that the agent talks to, basically. And this is the server. We give it a lot of stuff, virus configuration. And the server has only one exposed API. Everything else is just implementation of that thing. This is the RPC that is called by the agent via the RPC. And this thing basically polls Gitali, get project info, where on which Gitali server that repository is. Then it polls that repository. On a successful poll, when commit is a different commit, we basically start sending the response stream, the header. We have header, object, and trailer. So we send the header, then we send the body as 0 or more object messages, and then we send the trailer. Yeah, that's how the server works. This thing that sends the body basically reads
files in the manifest.
Yeah, fetches files from Gitali using gRPC API and uses some filters to enforce various limits and so on. Yeah, that's how the server works. Nothing super fancy here. Error handling, blah, blah, blah. But that's the logic.
Nice. Yeah, I mean, very useful information. I think I got a good picture of how these work.
Cool.
We're out of time actually. So,
yeah, I think we are out of time. We can look at other modules next week, actually.
Sure, yeah.
There are other interesting things. Like most of them are not interesting, but this one, reverse tunnel and Kubernetes API, these are very interesting.
I think the reverse tunnel will be one I'm interested in next.
Yep. Okay. Right. I will stop the recording. Thank you, people who watched this. Let me stop it.